get grades pretty quickly. When I was back in the old days, when we had to walk uphill to school and all that sort of thing, we didn't get grades until like after the first of the year. Our professors really took their sweet time to grade. But you, I think, get yours the Monday after finals. Okay, let's take a look at some announcements here. We've just finished going over the exam. You have one more assignment, and it's due Friday by noon. We started talking about the energy equation on Thursday before the Thanksgiving break, and I think that assignment's been posted for a couple of, well, since then. And at the end of today's class, I'll spend a moment talking about one of those problems just in case there's any questions and we need to discuss that particular question. But we'll cover everything you need to do except for one of the last problem we won't get to until Thursday, and so that's why the assignment itself is due on Friday. Okay, so it's probably been a while since you were thinking about the energy equation, and just to dust off the mental cobwebs, I wanted to give you this in-class exercise, and we're going to see if you can write the energy equation from memory. It would be interesting to see if we crowdsourced and took, like a democratic vote, what the energy equation would look like. They say there's wisdom in the crowd. All right, so the three terms of Bernoulli's equation: pressure head term, velocity head term, and elevation term, with some slight differences. Remember that in the case of the energy equation, we're adding the kinetic energy correction factor, alpha, and that's because if we use the average velocity, we're going to be underrepresenting how much energy is tied up as velocity head. And so that's the other difference, is that V bar means average velocity. So those three terms are the places where the energy exists at location 1 and location 2. Now up on the whiteboard I drew the same arrow that I've got sketched here. Just a reminder that the 1 and 2 has a direction notation, that we assume flow goes from 1 towards 2. And that's important because we're going to put other terms in the energy equation, and pump is on the left, turbine is on the right. And the reason why is if the water is going from 1 towards 2, something that adds energy needs to be on the left-hand side of the equation if we're going to know its residual effect at location 2. In other words, what we're saying is that as the water goes between 1 and 2, a pump would add energy. So how much energy there is at 1 is, how much energy there is downstream at location 2 is the amount that there was at 1 plus what was added by the pump, but then minus any losses that occur or any energy that's extracted by a turbine. So that's why those are on the right-hand side of the equation, is that both the turbine term and the head loss term will reduce the amount of energy that's available at 2 to go into the pressure, elevation, or velocity head term. And of course we can break H sub L down into 2 further subcomponents. Do you remember what those constituent terms are? Good. So head loss, H sub L, is the local losses and the frictional losses. Frictional losses you saw in person when you were doing the pipe friction lab, and local losses we're doing this week in lab, looking at the fittings. So let me just scroll down a bit, and a bit of explanation about what are the different terms on the right side compared to the left. And so the difference is, there's some things that are the same. Pressure, velocity, and elevation terms are the same. But this explains why we put the pump head on the left, and on the right, turbine head and losses. Okay, now what about this picture? Is it a pump or a turbine? If we know the water is flowing from left to right, we can tell that because of the arrows. So the water's going from this tank to that tank.
Is that a pump?
You say it in the form of a question.
No, it's a pump.
It's a pump.
Yeah.
You're right. How did you know it's a pump?
Well, it's because it has to get higher elevation.
Exactly.
It needs more energy.
Yeah, the only way water can flow uphill is with a pump. So it's a pump. So if we were going to look at it from the terms of the energy equation, you know, at the tank surface, there's no pressure, there's no velocity. You've got a certain elevation, plus the pump head is going to overcome whatever pipe friction occurs and whatever local losses there are. So the pump is adding enough energy to overcome two things, the losses and the elevation difference. So that's how you'd know how much pump head you need to add, is you'd ask, well, what flow rate is it going to be? And so for a certain flow rate, that would tell you how much energy loss there is. And then there's also the delta Z that has to be accounted for. Okay, so I'll pause again and allow you to consider these three concept questions on the back of the first page, and then try applying the energy equation with problem solving on question 2, where it's asking what will be the flow rate when we know the pipe length, the elevations, and we haven't yet done local losses. Well, I think the 319 lab that met yesterday did. But let me just point out that when we have an elbow and it's specifying the radius to diameter, and then we also have water that's exiting to a tank, on the back side of the equation is some information where you can find K values. And H naught is K times the velocity head, B squared divided by 2G. So in that problem solving question, when you get to it, you're going to have the friction losses defined by the Darcy-Weisbach equation, FLV squared divided by D2G. And then the local losses are going to be cumulative. There will be two local losses. There will be the elbow local loss and the discharge local loss. And so what I'd like you to do is take a look at the table that's on the back and see if you can find some information that would tell you what K value should be used. I'll break in just to clarify that before you do all the calculations, because I wouldn't want you to go through and find the answer based on the wrong K values. But I will pause for a moment so you can do those first concept questions and then start setting up question 2. Okay, so there's the K value at the discharge, at the elbow, and at the inlet. The K value for the inlet you can get from the table for a contraction. So it's effectively a contraction with a 180-degree angle, and the D2 to D1 is 0, meaning that you had an infinitely large tank that's going down to an enclosed pipe. And so K1 at the inlet, you should use 0.50 for the K value. And the expansion at the end of the tank is similar to that. So if you look at the expansion coefficient where the angle is 180 degrees, so it just means that a pipe terminates into a large tank and all of the velocity head that existed is just suddenly lost. And so this expansion coefficient of 1.0 accounts for that. And then the elbow that you can get the K value for a radius to diameter of 1 is going to be 0.35. And since the velocity is the same at all of these locations, the pipe diameter is going to be constant, then we are allowed to just add up the K values and multiply it by the velocity head. And so it's going to be 1.85 is the sum of the K values. And then you can multiply that by V squared divided by 2G. If you look at the K values on the table, the radius of curvature, where it's a very abrupt transition, so 1 means that the radius is very short relative to the diameter of the pipe. So that means it's going sideways and then almost instantaneously the flow is going down. The K value of 0.35 means that there's going to be more energy loss than if the transition was more gradual. So the R to D of 2, meaning that the radius of curvature is longer and the transition occurs more slowly, that reduces the K value, so less energy is lost during the more gradual transition. It starts going up again though. If you look at 6, 8, and 10, if the transition is too long, then what they're accounting for there is that a lengthy transition is going to introduce a frictional loss. And so it's kind of reducing the local loss effect, but increasing the amount of energy loss due to a more lengthy pipe. So besides the elbow, there's the inlet and the outlet we already talked about. And so other factors besides the fittings that can influence the rate of energy loss is, think about the roughness of the pipe. A very smooth pipe, like one that's made out of plastic or drawn glass tubing, is going to reduce the amount of energy compared to a rough pipe, like a rough concrete pipe, which is often used for sewer situations, or a pipe that's made out of cast iron would have a higher roughness. And of course, increasing flow velocity, since the velocity is squared in the friction loss term, then that's going to also have an effect on the rate of energy loss, as does the pipe diameter. If you consider what goes into the Darcy-Weisbach equation, those 3 factors also account for the rate of energy loss. Now, pipe length would not change the rate of energy loss, because the word rate is implying it's how much energy loss there is per unit length. And so the rate of energy loss is unaffected by the length of the pipe. Okay, so for the calculations, if we add up the K values like we saw on the board, it's going to be 1.85 is the sum of the 3 K values, the one at the entrance, the exit, and the elbow. And then substituting the given information into the Darcy-Weisbach way of estimating the friction loss, we've got the friction loss coefficient of 0.015, the length of the pipe, the diameter, and then 2g also down in the denominator. So when you solve for the velocity, it should be 2.233 meters per second, and then we can substitute that into the continuity equation, finding the area, and get 0.281 cubic meters per second. So by a show of hands, did other people also get 0.281? Good. All right. Okay, so that's from start to finish the application of the energy equation, kind of trying to remember it, understanding why certain terms are on the left versus on the right, and then implementing it to find out what would be the flow rate if the driving force is this pump that's lifting the water and overcoming friction losses and local losses. And you can tell that of the two, the friction loss is a much greater drag on the flow than the local losses are, and that's why they sometimes call these local losses minor losses, is that in comparison to the magnitude of the friction loss, the local loss is a very small part of it. In this case, looks like about 4%, 5% of the losses come from the bend, the inlet, and the outlet. Okay, so that is when the head loss can be calculated based on a known length, a pump head that's being added. We've seen a problem before where we had a horizontal pipe and we were trying to calculate what would be the head loss for a horizontal pipe. But one of the things that can confound pressure measurements is if we have a sloped pipe. So consider the case of we have two tanks connected together and water is flowing from the tank in the west towards the tank in the east. But because there's a slope in the pipe, any pressure measurement we take is going to be affected both by frictional losses and also by the delta Z. And so in this example, we measure the pressure at location 1, which is upstream, and location 2, which is downstream. And the pressure difference between the two is 86 kilopascals, meaning that the pressure at 1 was greater than the pressure at 2. Well, the pressure at 1, if it was static conditions, the pressure at 1 should be less than the pressure at 2. Because if we had static conditions and the water is just in these tanks and the water level is the same on the left and the right, because of the elevation difference, then the pressure at 2 would be greater. But what we see is that the pressure at 1 is greater, and so there's a head loss effect and there's an elevation change effect. And so what we can do is just substitute into the energy equation and kind of tease out how much of this pressure change is due to the elevation and how much of it is due to the head loss. And so that's what I'd like you to do is, at location 1 and location 2, we don't know the diameter of the pipe, so we don't know the flow rate, we don't know the diameter, but since the diameter is the same, V1 and V2 are going to cancel out. So being able to do that and also canceling out because we see that there's no pump and no turbine, both the turbine term and the pump term are canceled out. And so what we're left with is the pressure terms will be there, the elevation terms will be there, and the head loss term is what we're trying to solve for. You're going to have to calculate the z's based on the slope. Okay, between 1 and 2, there's no pump, no turbine. Now there could be a pump and a turbine in the system before and after 1 and 2, but as long as it's not between them, then we don't apply it in the energy equation. So we've measured the pressure between 1 and 2, and so it's just between those 2 points where we're looking to see if the pump or turbine term should be included. We don't know anything about the diameter of the pipe or the velocity of the flow, so we can conclude just from the picture that's given that the pipe diameter is constant, and that's why we're able to cancel out the velocity head terms. And so when you rearrange the energy equation to solve for the unknown head loss, it's going to be the pressure change that was measured and then the elevation difference between location 1 and location 2. And so in total, as the water flows through the pipe, it's 25.12 meters that's lost. And so we know that because the pressure change should have been other than what we measured. You know, the pressure change, there should, if there was no losses due to pipe friction, then the pressure at location 2 would be greater. But since it's less, we attribute the difference between the two to be because of the losses. Any questions about those calculations? Okay, let's take a look at how to handle the energy equation when we want to calculate power, like in a hydropower scenario. What we have here is an elevated reservoir where water is flowing from an elevated reservoir down to a lower location. And the water flows through a penstock and into a turbine that extracts the turbine head and turns it into electricity. If we know the elevation of the upper reservoir and the lower reservoir and have some function or given head loss that tells us for the flow rate that's in question how much energy is going to be lost as the water goes through that conduit, then what we're able to do is calculate the amount of power that can be generated. And now this is the power equation assuming perfect efficiency, assuming that no energy is lost that all of the energy that's extracted from the fluid is turned into electricity. But in reality, there are inefficiencies. But just to illustrate, to make a point, I'm first going to illustrate the calculations that you'd follow if it's 100% efficient, and then what would we need to do if it is instead only 70% efficient, like if that's the combined inefficiency of the generator and the turbine together. So the first thing that we're going to have to do is to find out how much pump head is available, how much turbine head is available by substituting it into the energy equation. So we'll do that here. So location 1 is going to be the upper reservoir, location 2 is going to be the lower reservoir, and the energy equation, the pressure head, elevation head, and velocity head at location 1 plus h sub p is equal to P2 divided by gamma plus Z2 plus V2 squared divided by 2G plus H sub T and H sub L. All right, so we have the Z1 defined by the upper reservoir's water surface elevation. So Z1 is 1324.4 meters. P1 is 0 since we're working at the water surface. V1, the velocity in this reservoir is 0, although the velocity through the penstock isn't 0. Location 1 is at the reservoir, so that's 0. Between the 2 points, there's no pump, so H sub P is 0. There is a turbine, but no pump. Z2 is 1191.9 meters. V2 is 0, and P2 is 0. The average velocity of flow through the pipe is 2.4 meters per second, and since we know that the diameter of the pipe is 1.5 meters, that allows us to calculate the area of the pipe, pi 1.5 meters squared divided by 4, so the diameter is 1.7671 square meters. Now, substituting everything that we have into the energy equation, the pressure head term cancels out, the velocity head term cancels out at both locations. So it's this elevated reservoir, 1324.4 meters. There's no pump, is equal to the elevation at the lower reservoir, 1191.9 meters, plus the turbine head and the losses. Oh wait, the losses are given directly, 5.4 meters. So in the energy equation, we're saying how much energy is left for the turbine to extract and use. So the difference in elevation, upper minus the lower, is going to be part of the energy that's available. But you also have to leave some of the energy to satisfy the losses as the water is going through that penstock. And so what we'll solve is that the turbine head is 127.1 meters. So that's the elevation difference minus the losses, and that's how much the turbine can extract and then turn into power. So that's the energy equation, and now in the power equation is where we'll incorporate the H sub T that we've just calculated, the unit weight of the fluid, and the flow rate through the pipe. We have the pipe velocity and the pipe area. So let's calculate Q. It's going to be A times V. Okay, so that's the 1.7671 meters squared times 2.4 meters per second. So that flow rate is 4.24 cubic meters per second. And now part A, we're assuming perfect efficiency. So we don't have to worry about any losses in the conversion. So the power is going to be the flow rate of 4.24 cubic meters per second multiplied by the unit weight of the fluid, in this case water. I'll put in the standard unit weight of 9810 newtons per cubic meter, and then the turbine head that this turbine can extract. So it can take out 127.1 meters of energy, and when we multiply all that together, what we get is 5.29 times 10 to the 6th watts. And so about 5 megawatts is what this hydropower station is capable of generating, assuming it's perfectly efficient, that there are no losses. Okay, so in case B, if we do want to account for some losses and it's 70% efficient, if it's 70% efficient, is it going to generate more than 5 megawatts or less than 5 megawatts?
Less.
So should we multiply or divide by 0.70? Multiply, right. And so if you have a turbine, then what you do is you multiply by the efficiency factor. But if you have a pump problem, then you divide by the efficiency factor. Because in the case of a pump, the question is how much power is needed to spin a pump. And so there's the power that needs to go into the water, but then you're going to have to put even more power into the motor and the pump assembly in order to get that energy into the water. So the rule is that when you have a pump, divide by the efficiency factor, and for a turbine, multiply by the efficiency factor. And sometimes the efficiency factors will be specified individually, like they'll give you one efficiency factor for the pump and one for the motor, and so you just multiply them together. And it's a cumulative effect. So in this case, for the 70% efficient, let me just show you the calculations for that one. All right, 70% efficient, you just multiply the 5.29 megawatts by 0.7, so it would be 3.7 times 10 to the 6th watts is available if it's 70% efficient. Okay, in the time that remains, I want to give you a little bit of guidance on this homework problem.
I was going to ask you about that.
Well, I'm showing it because you asked me about it. Yeah. All right. So in this one, I'm telling you how much head loss there is per meter of pipe length. And so, if you're applying the energy equation, the first place that you need to apply it is between the tank and this jet of water. Because if you apply it from the tank and the jet of the water, you know a lot of things. You know the pressure of the fluid will just be atmospheric at both of those two locations. You've got the Z defined for both of those locations. There's no velocity at 1, but it still will, the flow will have velocity at 2. And so whatever that flow velocity is at 2 exists and remains as the flow is coming out of the pipe. So the way that you're going to find the velocity is that you're setting up the energy equation, and the losses are defined in terms of the length of the pipe. So you can see it's 35 meters plus 3 and another 5.5, and so add up all of that pipe length and multiply it by 0.152, and that tells you what's the H sub F. So if you substitute into the energy equation, the only unknown is going to be the velocity head that exists at location 2.
Do you mean H of L, not H of F?
No, because it says to neglect the local losses.
Okay. What about the energy adjustment value?
The kinetic energy correction factor?
Yeah.
Well, conditions have to be really specialized for it to be laminar flow. So I think it's safe to assume that alpha will be 1.05, which is the turbulent flow kinetic energy correction factor. And you can verify that once you calculate the V.
Okay.
You can put it into Reynolds number and verify that conditions are turbulent.
All right. I just need to make sure. You know, by the way, when I was trying to measure the change in elevation, the exit elevation plus the 5.53 is higher than the tank.
I'll have to double check that. Okay, that's it for today. I will see you in class on Thursday.
Or today during lab.